So whenever you see a problem P that looks like the rod cutting problem, like the rod cutting problem, you may be tempted to think, well, can I apply dynamic programming to my problem P, right? Before we apply dynamic programming to a problem, we need to make sure that the problem P exhibits two properties, number one and number two. The first property that this problem P must exhibit is the optimal substructure property. And the second property that this problem must exhibit is the overlapping subproblem property. So any problem P where we would like to apply dynamic programming must have these two properties in order for the problem to be eligible to apply dynamic program. Now, if you remember, here's the rod cutting problem, the subproblem graph for the rod cutting problem, where the rod cutting problem for a length of rod of length 4 depends on the solution to the subproblem for a length of 3, length of 2, and so on. Now, what the optimal substructure property means is that the solution to a problem, let's say the problem of length equals to 4, must contain within it the solution to its subproblem. Say, for example, a smaller length like L equals to 3 or L equals to 2. So if our problem is such that our problem P, big problem P, can be broken down into subproblems P1, P2, P3, and so on, such that solving P1, P2, P3 eventually solve the main problem P, then we say that our problem exhibits the optimal substructure property, just as in the case of the rod cutting problem. The next property that we would like to see in a problem is the overlapping subproblem. So looking back at the rod cutting problem, what we know is that to solve a rod of length L equals to 4, we need to solve L equals to 3, L equals to 2. Now to solve L equals to 3, once again, we need to solve L equals to 2. So what we have is this subproblem and this subproblem overlap. That is, if we were to use recursion to solve this problem, if you remember, we actually solve these two subproblems. We treat these as two separate subproblems and then solve them twice. Now, in order for dynamic programming to apply, what needs to happen is that there should be many overlapping subproblems like these. For example, here's another subproblem, and we have the same subproblem here. So in other words, overall, what we want to see is the total number of unique subproblems must be way less than the total number of subproblems. So basically, if we have a scenario where recursion solves the same problem again and again, that's the only sort of scenario where dynamic programming applies. So these are the two key ingredients that an optimization problem P must exhibit in order for dynamic programming to apply. To better understand the two key ingredients that a problem needs to exhibit in order for dynamic programming to apply, let's look at two problems. One problem where dynamic programming is applicable, and the other problem where dynamic programming is not applicable. And these two examples will serve as examples to further understand when GP is applicable and when it's not. Say, for example, we have a directed graph, G equals VE, maybe something that looks like this, and vertices UV, two vertices U and V belong to our entire set of vertices. The first problem that we would like to take as an example is the unweighted shortest path problem. So the problem is, what we would like to do is find a path from, say, a vertex U to vertex B, consisting of the fewest edges. That is, since these paths are not weighted, that is, we don't have numbers associated with them, the challenge is to find the distance between A and E in terms of the fewest number of edges. So for example, here, if we were looking at the distance between A and E, then the fewest number of edges would be these two through B. So A, B, E would be the path that has the fewest number of edges, because if we went some other path, and this way the number of edges would be 1, 2, and 3. This way the number of edges would be 1, 2, and 3 also, and so on. Now, say for example, we pick a path, a vertex in the path between U and V, let's say A and B, and let's say that this vertex is W. Now, given, say we have a solution that the shortest path from U to V or A to E is via B, right? Let's say this is path P, the entire path is path P. And let's say we break the path down into two paths such that this becomes P1 from A to B, and from B to E, this becomes P2. Now the question is, can we argue that if P1 and P2 are two paths broken from P, where this node B or W here is in the path P, can we argue that P1 is the shortest unweighted path between A and B, and P2 is the shortest unweighted path between B and E? So I guess it's pretty clear to you that if this wasn't the case, then P wouldn't be the final solution, right? So if there was a shorter path from A to B, then P would not be the optimal solution. So clearly, P1 and P2 are also optimal solutions to the sub-problems. So this is an example where we can look at the problem and say, well, the substructures or sub-problems actually sum up to solve the main problem, right? So this is a case where we can argue that the optimal substructure property holds true, and that's why such a problem can actually be solved using dynamic programming. Now let us look at a second example where the problem is finding unweighted longest path between two nodes. That is, what we would like to do is find a simple path from U to V consisting of the most edges, that is a path that has the maximum number of edges. So in this case, the path that may have maximum number of edges from A to B would be 1, 2, 3, and so on. So because this is an interesting problem, let's look at this separately. Now let us discuss how dynamic programming does not apply to the unweighted longest path problem. So to give an example of the longest path problem, say we have a graph like this, and we are interested to find the longest path between Q and T. So the longest path between Q and T could be either QRT or QST. So in order for dynamic programming to apply, our optimal substructure property must hold true. In other words, our solution to the longest path between Q and T must also contain the solution to intermediate paths. In other words, more specifically here, if QRT is the solution to our longest path between Q and T, what we would like to ask is, if we take an intermediate vertex here, Q to R and R to T, the question that we should ask is QR the longest path between Q and R? Or, and is RT, the whole thing, the longest path between R and T? So what we are just checking here is, does the longest path between Q and T also contain within itself the solutions to intermediate vertices? So now let's check, is QR the longest path between Q to R? So from Q to R, is this the longest path? Obviously not. The longest path actually is QSTR. So QSTR. So this is not the longest path between Q and R, and this is also not the longest path between R and T. In other words, what we see here is that the optimal substructure property does not hold true for the longest path problem. A problem does not contain within itself a solution to the sub-problems or the solutions to the sub-problems. And that's why the longest path problem is a problem where we cannot apply dynamic programming. Now that you understand that given a problem P, we can check whether this P can be solved using dynamic programming or not by using the optimal substructure property and the overlapping sub problems property. Say, for example, you do have a problem that exhibits both of these and you want to solve the problem P using dynamic programming. What are the steps involved for us to develop a dynamic programming solution to this problem P? The first thing that we want to do is characterize the structure of an optimal solution. So given a solution to a problem, you want to visualize or somehow see how the optimal solution looks like. So for example, for the rod cutting problem, optimal solution looks like 4 depends on 3, 3 depends on 2, and so on. So we want to characterize this. We want to understand it, discuss this, and then maybe visualize and see how the structure of the optimal solution looks like. Next, once we see this, next what we want to do is recursively define the value of the optimal solution. This is looking at the structure of our solution and obtaining something like this one which recursively defines how the optimal solution would look like. Next, we want to compute the value of optimal solution using a standard, something like a bottom-up fashion, and obtain an algorithm that gives us the optimal value. For example, for the rod cutting problem, the maximum revenue, and so on. Next, so this is the core of the dynamic programming algorithm. But then what we know is in order to obtain an optimal solution, that is, for example, in the case of rod cutting problem, to find out where to make a cut, you want to improvise the dynamic programming solution. So you actually print out the actual solution that we're looking for example, where to make the cut.